Okay, what's up, everybody? Welcome back, Friday. Online students, hey. All right, so let's get into it. We are actually running well ahead of schedule. Great news. This is nice. Let's kind of keep it going, hopefully. That'll make things easier instead of harder. Last time, we talked a little bit about instantiation, quantification, and predicates. So if you remember, predicates were these little tools we had to turn statements that were almost propositions into propositions. That is, you can think of it like a predicate is a proposition, but you took part of it and you erased it and you put like a little stand-in, like a blank, You fill in the blank, you get a proposition. As long as the thing you fill in the blank with makes any sense in the first place. So when we talked about this part, we said, hey, we got to talk about universes or domains of discourse or whatever fancy term you want to put for the bag of options you have to plug into that empty spot. All right, cool. So we talked about what we can do. We can actually take one of the options and put it in and get a proposition. We can select a particular instance, this process we call instantiation, choosing a value for a variable. We could also talk about all of the different choices. So there were two primary ways we could do this. One of them was existential quantification. The other one was universal quantification. Universal quantification, we say, this thing's true for all the choices. It doesn't mean it necessarily is. That is, you could make a statement like that and it could be false. But that's what universal quantification is. Existential quantification, same business, except instead of saying for all of our choices, you say for at least one choice. And we talked kind of briefly about how these are the only real ones you need. Even instantiation you can see as either universal or existential quantification, provided you restrict your universe of choices down to a very small subset with only one option, right? So, okay, cool, right on. Similar kind of things go on if you want to say like for at least two choices. Well, if you change your universe to, instead of being the things you started with, but instead pairs of things, well, then you could say there exists at least one pair of things. So as long as you're flexible with what your universe or domain of discourse is, you can use existential and universal quantifiers to represent basically any quantification you might want to do. All right, fun, cool. Now, every example we did last time, we did some Venn diagrams, we talked about syllogisms and stuff, but all of our examples involving quantification were effectively just about single variable predicates. That is, predicates where there's only one blank to fill in. But we know that a lot of the times there's more than one blank to fill in, yeah? So let's start talking about quantifying those guys. As you can imagine, quantifying statements with quantifying predicates with more than one variable has an ordering component. That is, if you're making a statement about for all things you can put in this slot and for all things you can put in that slot, right? It perhaps matters which thing you put first. Maybe that was a bad example with the for all, because the way I said it makes it sound like it can just go either way. But if we say, for instance, like an existential and a universal quantifier, perhaps order does matter. Let's do some examples. Let's see how it works out. And maybe it'll all make a little more sense. So let's start out with this example. Let's consider the predicate p of xy that is given by the statement x plus y equals 0. By itself, not a proposition, right? Not true or false, just a string of symbols. But if we take our universe for both x and y to be the set of all real numbers, then we can make this predicate into a proposition by quantifying the variables. Let's try this one right here. Let's determine whether for all x and for all y, p of xy is a true statement or a false statement, provided that the universe is the set of all real numbers for both variables. Notice the universes could be different for each one of the variables. Ooh, interesting. Okay. So, translating for all x, for all y, p of xy says for all real numbers x and for all real numbers y, x plus y is equal to 0. There's actually a slight difference here. Maybe I'm actually being slightly loose. This is ultimately equivalent to what I'm trying to say. But this and here seemingly has become inserted when it perhaps shouldn't be. It is how we would say it, I guess, right? For all real numbers x and for all real numbers y. But really what the statement is that for all real numbers x, like plug any real number x in, then the universally quantified statement that for all real y, p of that fixed x, y can vary, is true. Does that make some sense? That is, really perhaps the correct thing to say would be, for all real numbers x, it is true that for all real numbers y, x plus y is equal to 0. Does that make some more sense, what I'm trying to say there? We're throwing this and in here in a loosey-goosey way for a minute. I'll show you in a moment why this is a perfectly reasonable thing to do. But what this really says is, for all real numbers x, it is true that for all real numbers y, x plus y is equal to 0. Is this a true statement or a false statement? Pick a real number x. Pick the number x is equal to 0. Then the statement for that case becomes, it is true that for all real numbers y, 0 plus y is equal to 0. That's not true, right? There are numbers other than 0. Yeah? Okay. This is false. Okay. Another example, same, but now for all y, for all x, p of x, y. What does that say? Notice I'm switching the order of the quantifiers here from for all x, for all y, p of x, y, to for all y, for all x, p of x, y. What does this say in plain words? So translating, this says, for all real numbers y, it is true that for all real numbers x, x plus y is equal to 0. This is also false, right? It's effectively the same statement, yeah? Okay, maybe that's super obvious that it's effectively the same statement, but I think just looking at the symbols, it's not immediately clear necessarily that it should be, right? And maybe you're looking at it and saying, okay, I guess it is now, but what about different predicates, right? What's going on? Well, this at least maybe perhaps makes some sense of why we would casually, like, reading this, want to say, for all real numbers x and for all real numbers y, x plus y is equal to 0. Since it doesn't seem like the order matters, we can use some sort of a connective that doesn't care about order, right? Something like and. Like p and q is the same statement as q and p. Well, it's not the same statement symbolically, but they are logically equivalent. They have the same truth values. Yeah? Okay. So maybe that makes some sense why we would kind of instantaneously convert this in our heads to this. But there is an underlying thing going on. This is a slight diversion, I guess, from what's in the notes, and you don't have to write this down since I won't actually grill you on it right here. But this is an example of something that if you've taken some computer science classes, you may have noticed before or heard of before. It's a process called currying. I don't know where the origin of that name comes from, currying. The idea is that if you have a function of two variables, then a way of looking at this is that this is like a function that takes, say, for instance, an x and sends it to a new function. We'll call it f sub x of y, right? That is, you send an x to a new function where the x is fixed and the other input is the thing that can vary. You see what I'm saying? Another way of writing this, if you want to adopt some notation momentarily, I will not actually make you use this notation throughout, but the idea is something like the maps from the set x cross y, and I'll make these nice capital X's and Y's, to a set z. This is somehow, I'll put in like equal in some quotes right here, because what the heck do we mean by equal in this case? What is even the maps? I mean the things that send pairs, one thing in x, one thing in y, to something in z. These maps are effectively the same as the maps from, say, x to the maps from, let me write this slightly smaller so that the camera doesn't go off the edge. The maps from x to the maps from y to z. This is the process of currying effectively, is that you can take a function of two variables and by fixing one of them, obtain a function of one variable. That is, you can take something in part of your domain, fix it, and now you have a function that sends something from the other part of your domain to the same codomain. Does that make some sense? This is effectively what we're doing right here with our quantification. We're looking at something with two inputs, and we're like, hey, for all x, that is, fix any one of these x's. Now here's a universally quantified statement about a predicate that only has one variable. Does that make sense? It's like fix x equal to 3. Now I just have a statement about the y's, right? Okay, cool. So this process is called currying. It's super useful. And it's a good way to look at things, right? There's actually kind of a lot hidden in this process. It's like it's a fancy one. It's a cool one. But yeah. So side note, if you ever hear of someone talking about currying, this is what they mean. I don't know if you'll ever hear someone talking about currying. Maybe if you take a lot of computer science classes, you will. Anyways, back to it. Okay, so not too different there. But what if we flip to some existential quantifications? Will it matter? Will the order matter? Well, let's just keep the same one. Same. But now, with existential quantifications, there exists an x such that it is true that there exists a y such that p of xy. Okay. Translating, what does this say? Translating, this says there exists a real number x such that it is true that there exists a real number y such that x plus y is equal to 0. You see why we potentially love the notation of these backwards e's and upside down a's. As you can hopefully see, it is substantially shorter to write backwards ex, backwards ey, p of xy, than this garbage right here, right? Way easier, way better, way more straightforward and compact. But this is what it's saying. There exists a real number x such that it is true that there exists a real number y such that x plus y is equal to 0. That is, such that it is true that x plus y is equal to 0. That is the assertion of this statement. Is this true? Let's think about it. So there exists a real number x. So there's some number x such that there's another number y that you can add to it and get 0. This statement basically says that numbers have additive inverses, things you can add to them to get back to 0. Yeah? True. Okay, fair enough. Now let's do, well, I won't even belabor this point too much right here. But what if I switch this x and this y right up here? Put the y first, then the x. It's similar enough that I'm not going to go rewrite the whole thing, because all you have to do is switch the x's and the y's throughout. Still true, right? Yeah. Still just a statement about the existence of additive inverses. Okay, cool. Makes sense. Reasonable. Okay. Now, what if we start mixing quantifiers? Does it matter?
It does.
Indeed does. Okay. There's another way of looking at this, by the way, which is backwards currying. Uncurrying, you might want to think of it as, which basically says, hey, when I'm asserting that there exists a y and there exists an x, such that this is true, what I'm really asserting is that there exists one pair of x's and y's such that this is true. That is, if I think of p instead as a predicate of two variables, but instead as a predicate of one variable, but that variable is a pair of things, like an xy pair, right? Then I could make this into a single existentially quantified statement. Same business with for all. For all x, for all y, p of xy means that for all pairs xy, p of xy, right? Where now p is the predicate that takes, instead of an x and a y, it takes a pair xy. Does that make some sense? Okay, so hopefully that kind of makes some intuitive sense of why order doesn't matter when your quantifiers are the same. But can you do the same trick if your quantifiers are not the same? No. Ooh. Or maybe you can do something like it, but certainly not in so clear of a way, right? Not without changing our universes in a more substantial way. So let's look at another example, and let's start mixing quantifiers now. So, example, same business, but now let's do, well, I'll keep it in the same order as what we do in our notes. For all x, there exists y such that p of xy. Let's try it. What does this say? Well, what it says this says, for all x, it is true that there exists y such that x plus y is equal to 0. Okay, cool. Well, this is actually, I think before I said that this previous example said that there exist additive inverses. What I mean by that is that this one says there is at least one number with an additive inverse. This statement is the statement that all numbers have additive inverses. Yeah? Okay, it says that for any old number x you choose, there is some y that you can add to it to get 0. What is y? It's negative x, yeah? So, true. Now, what happens if we flip the order? This is going to get different. So, flip the order and say, here, instead of saying for all x, let's say there exists x such that for all y, p of xy, this says now, well, here, let me just erase the whole thing so I don't rewrite in a silly way. Now, this says there exists a real number x such that it is true that for all real numbers y, x plus y is equal to 0. Is there a number that if you add it to anything, you get 0? No, there isn't. Not a real number, at least. Yeah? False. something's different here. You flip the order of the quantifiers and now it matters, right? Crazy. What's going on? What's the business with this? The easy intuition for it is that when you are making a existential quantification on x and an existential quantification on y, you are really just making an existential quantification about a pair. Same thing with universal quantification. You said for all x and for all y, what you were really saying is for all pairs x and y. Yeah? Now you're making statements when you mix quantifiers that are not about pairs, but about much larger subsets of the domain. That is, when you say there exists an x such that for all y, it means that there is some x, so if you put it in like the first argument of the pair, no matter what you put in the second argument is true, right? That is, we're making a universally quantified statement about something like a line, right? Another way of putting it, well, I don't want to belabor the point, but effectively, you see what I'm saying is that like one of them is being fixed and the other one can vary, and so now it's not a statement about a single member, nor is it a statement about all of them, but instead it is a statement about a very particular type of them, right? Something like like if you like fix an x and let the y's vary, if you think of graphing this, it's like a vertical line, right? Or if you fix the x and let the y and let the x vary, it's like a horizontal line, like in regular old number world, right? So while before we were making statements about everything or just one thing, now we're doing this weird thing where we're making statements about lines, which is, as you can imagine, probably harder to deal with, yeah? So a big lesson of it. Quantification of a predicate with more than one variable is possible, not too bad to do when the quantifiers are the same, but some care must be taken when they're not the same. Yeah? Reasonable. Okay, cool. So from this, the next thing that we want to touch on is negations. So section 1.4, look at us. We're well ahead of schedule. How exciting. A great way to end your Friday, knowing that you are quite well ahead. So here is, I don't think we'll get through all of negation today by any means, but here's the start of it, the idea of what we're going to talk about and what's going on. Okay, so section 1.4, negations. Here's the name of the game. You got a statement about something. You want to know what is the not version of it. That is, what is the statement with all the truth values flipped? But you want to know more than just, well, hey, put the not symbol in front of it. You want to know what is an equivalent statement that is not just fully negated, that has the same truth values. Yeah? Which is reasonable to do. It kind of becomes hard when your proposition is a compound and full of quantifiers, right? That is, let's think of some basic examples. If I say statement 1 is true and statement true is 2, what is the not version of that?
Both are not true.
Is it the both are not true? Or would it be,
One of them is not true.
yeah, something like that. Let's see. Let's try. Let's try some of this stuff. Okay, so here's an idea. So here's a quick theorem. So, given any propositions, P and Q, not P implies Q, so this whole statement, the not P implies Q, or actually let me write this in the next line so it doesn't. This is the same as P and not Q. Does that seem reasonable to you? Perhaps. let's, before we jump into this, take a moment, since we have a little extra time, to try something more simple. Let's start with something a little tiny bit more simple. We'll get to some of this stuff later, but let's do something easy first. So here, quick idea. So let's do, here's P, here's Q, here's, say, P and Q. Okay, P could be true, true, false, false. We could go true, false, true, and false. Okay, P and Q, when is it true? When both are, right? Yeah? Okay. So let's try something else. Can we come up with, and now if we go and negate this, what we'll end up getting, I'm going to write this out because, well, it's easy enough, but everyone can know what it's going to be. It should, hopefully, make some sense of what's going to go on here. So in this situation, if I say not P and Q, what's the business? Well, you're just going to have the opposite truth values of P and Q. Okay. So if P is true and Q is true, this statement is false. But every other time, it is true. Okay. Let's think about what this could be. What is something that works sort of like this?
Not to P or not to Q.
Something like that, exactly. Yeah, totally reasonable, exactly. So here is the claim that has been made. The claim that has been made is that not P and Q is the same as not P or not Q. Reasonable, perhaps? Let's think about it. So an or statement, when is an or statement true?
If exactly one is true.
Or if at least one is true, yeah. If it's an inclusive or. If it's an exclusive or, it would only be one. But we're going to use inclusive ors. So if at least one of the things is true, the or statement is true. The only time the or statement is false is if both the things are false. Here I've got something where I've got all trues and only one situation with a false. Kind of similar to an or, right? I just have to make sure that the stuff I'm punching into the or is the right stuff. Yeah? Okay, so let's try it. Now, if I do say like not P and not Q, this is going to be kind of a long and extended truth table written in a somewhat disjointed way to hopefully make the point clear. Not P will have the opposite truth values of P. So this will be false, false, true, and true. Not Q will be false, true, false, true. Now, if I go not P or not Q, what do I get? Well, false or false is false. Yeah, it's the only situation where we get a false. But in every other one of these, I have at least one true. Hey, check it out. They are the same, right? You're correct, exactly.
Could you describe like if P then Q and then just take the inverse of, or like just negate that? Like you're say like.
Yeah, totally. That's exactly what we're going to do. Yeah, right on. So starting, I guess, with this negation of like a, an and statement. It's maybe a easier one. I don't know if it's easier, but hey, it's there. Okay. Can we do the same kind of process with a different statement? Let's see. Let's try. Okay, so what if we do say like, instead of P and Q, what if we do P implies Q? This is a great review because everyone forgets what it should be. Okay, P implies Q. When is it true? When is it false?
P is true and Q is false. No.
Yeah, when P is Q, or not when P is Q, when P is true and Q is false, right? Yeah, exactly. That is the one case where it is false. Every other situation, it is true. Oh, this is looking reasonable to deal with, right? If anyone has forgotten this, just think of if it is snowing, then it is cold, right? Okay. If it's not snowing, does that mean it's not cold? No, it could still be cold. It could just not be snowing, right? So, hey, it could be false and the second thing could be true, and that could still be true. It could be not snowing and not cold, but it's still true that if it is snowing, then it's cold, right? Last situation, so on. The only way the statement would be false is if it was snowing and it was not cold, right? But that doesn't happen. Okay, cool. So, hey, P implies Q. Let's do not P implies Q. So not this whole statement. We just flip all the truth values. False, true, false, and false. Similar to the situation we had before, now we've got something where everything is false except for one true. Agreeable? Yeah? Okay. Now with ors, we know that when we do some ors, we end up with a situation where the only time we have false is when both things are false. Yeah? Okay. So here, we've got kind of the backwards, right? What about ands? It's only true when both are true, right? Every other time it's false. So this kind of looks like an and, right? You got one T and three Fs. Looks like an and to me. Yeah. It's a weird way of looking at ands, right? But hey, it's how it works, yeah? So let's just figure out the and statement where you get a T where T is true and Q is false. Well, P should definitely stay true, perhaps. Yeah? We just need to make Q true. Yeah, negate it. Exactly. So what if I said P and not Q? Okay, let's run through it. So I've got P, I've got not Q, so it's false. I've got P, I've got not Q, true. P, not Q, false. P, not Q, false. So I get false, true, false, false. And hey, FTFF, FTFF, the same statements. There is the tedious truth table version of this proof, right? Of the theorem we stated. But you kind of see like the idea of how you might come up with these sorts of rules. Yeah? If you were just, starting over, reborn into the body of someone in Athens or something, and you have to come up with propositional logic from scratch, right? Okay, here's an easy way to do it. Just match patterns, right? Go like, hey, ands have one T and three Fs. Ors have three T's and one F. Okay, so you can just kind of start matching it like this, yeah? Build it together like Legos. Okay. Hopefully there's a more sophisticated way of doing things than this, right? Hopefully there's a better way of going about all this than this. I don't want to have to negate a statement like P implies for all X, P of X, or for all Y and all Z, Q of XYZ implies M of X. I don't want to have to make a truth table here, and some of these are even quantified, even worse. How the heck do I even deal with truth tables for quantified statements and everything? It's going to get even worse. Oh man, what are we going to do? Well, let's come up with some sort of a way to deal with this in a more structured, reasonable approach. I've somewhat hinted at these sorts of things for a while. We're going to have to come up with a formal method of putting pieces together and deriving new statements, kind of similarly to how you can, put numbers together and get new numbers with something like addition, right? A formal structured way of putting premises together to get conclusions, stuff like that. Since after all, if we're making a statement about negations, we're saying, like, premise this, conclusion this, right? Let's try. Okay, so theorem. So the idea is, actually, let me look at my watch. Well, okay, here, we'll start with this. Given any propositions, a little longer. P and Q, not P implies Q, is the same as P and not Q. Maybe I should put left and right arrows here to make this relatively clear what I'm saying. Yeah. So you could go through a truth table. You could do what we just did where we showed they have the same things. And then you could do the tedious last step of showing that since these things always have the same truth values, the column for this one would just be all T's. That is, you'd show it's a tautology, making this statement a true statement. Yeah?
Is that supposed to be not P and not Q? In the...
Not P and not Q? Is that? I don't think that's what's in the. Was that in the truth table? No, you can even see the ghost of it right here. It was P and not Q. Yes. Do you believe it? See how suddenly all of our intuition begins to slip away, right? Like, so far I hope everyone has felt mostly like, like, oh, like most of these statements, if you actually just write them out and you go, hey, like, is there a number x such that for the number y, this thing plus this thing, right? It feels easy, but suddenly we've lost ourselves in a sea of symbols and it becomes unclear how we should deal with them. Let's get at it. This is normal. This is how it should feel. We build up simple blocks and then as suddenly we realize that we can build kind of crazy towers of things that we don't know how to deal with. It's great. So let's prove this. So to see this is true, we can make a truth table just like we did, right? Now let's do it in the more structured and organized way that was not just hopeful pattern matching, yeah? This will, I imagine, be slightly more instructive because it will make it clear how you should go about this if you already know the thing you want to say. So the idea is that I effectively want to show that this thing, not P implies Q, and this thing have the same truth values. Probably the most coherent way to do this in a table is to start out, well, every time with your P and your Q. And now we're going to go across and we're going to keep adding columns until we fill everything up. And hopefully this is super visible. True, true, false, false, true, false, true, false. And now what we're, now, okay. I'm not going to let it happen again. And now, there we go. Yes. I hope the audio has been here the whole time. I think I ducked down too low and I lost it. That is a very short range if I'm losing connection over that. Weird. Anyways, the whole point is that we should build to each one of these statements, and then ideally, if we want to make this like nice and easily, well presented, put them next to each other, something like that. Yeah? So you can see the two columns are the same. Okay, so what ingredients do we need for each of them? Well, here I need an implication and a not. Okay, here I need a not Q. And then I do the and version of it. So what I'm going to do is I'm going to do the not Q really quick next to the Q. I'm going to say false, true, false, true. Super easy building block. And now with each of these pieces, I can put it all together. So I'm going to go, okay, what about P implies Q? Just like we did before. Well, here, true implies true, or that's true. True implies false, false. But otherwise, we've got trues all the way down. And then we're just going to not it. Now, when we not it, we can go false, true, false, false. And hey, finally, we can do P and not Q. Notice we've got all of our building blocks. We've got our P's, we've got our not Q's. So this is just adding one thing, right? Now going through it, we say P and not Q, true and false, that's false, true and true, that's true, false and false, that's false, false and true, that's false. So it looks, as we would hope, the exact same, false, true, false, and false. Now, if we really want to show this statement right here, we could do the annoying extra step of adding a column that looks like not P implies Q, if and only if P and not Q. And we could add this as one extra column, but we already know what we're going to get here, so usually people don't do this pedantic extra step, since the if and only if statement is true. This left-right arrow, this arrow pointing in both directions, is true only when the things have the same truth value. And hey, look, same. So this column, if you're doing like a proof by truth table, you can usually skip the last column because all it is going to be is just a bunch of T's. And, well, I guess it would be more technically correct to include it. We usually don't make you since that seems tedious and annoying. Reasonable? Okay, basically the same as the truth table we constructed before, but hopefully done in a slightly more organized way. And I think it's important to talk about that, right? Because as you start to build these big old truth tables out, dealing with things, it is easy to get yourself lost and confused, to look at the wrong column, to be not sure how to do things. And this is, I guess, in like many ways, largely like aesthetic preference, right? But then again, I guess much of proofs is exactly that. It's more like regular writing. What you want to do is you want to probably end up so that your last two columns are the things you want to show are equivalent, or the statements you want to, something like that, right? Then you want to look at these statements, take their building blocks, and fill the preceding columns with them. Ideally, if you negate something, then the column right before it is the thing being negated. Yeah? So when I say not P implies Q, the column right before it should be P implies Q, and so on, right? Reasonable? Cool, okay. What other statements can we prove? There's a lot of them. We will get into these, but looking at my watch, I see that we're very close to the end. And hey, it's Friday. Get out of here. Have fun. Have a great weekend. If you have any questions, send me emails. Stop by. Well, I guess no office hours today, but next week, whatever. I'll see you around. Have a good one.